Morning, guys. So yesterday we started introducing our relative strengths table. Basically, we refer to something as strong if it's 100% associated. That one will definitely be a one-way arrow. The calculations afterwards will be a lot easier. For weak acids, technically it would be anything less than 100%. We're probably talking something more like 5% ionization, 5% dissociation. Although in that weak acid section or weak base section here, there will be some that are still relatively better than others. So I'm just going to give you a quick practice question here. We'll have another look at that table. So just for warm up here, first one just for practice, I want you to write the complex equation. So write the full equation. Remember the table has everything simplified for you. Write the complex equation for, let's do here, HSO3 minus as an acid, and let's do HCO3 minus as a base. Okay, so we have those two expressions there. Later on, what we're going to do is we're going to, armed with those two equations, I want you to see if you can complete this equation. What if I put HSO3 minus in the presence of HCO3 minus? Would you be able to predict for me which way the proton gets transferred? So again, I encourage you just to pause the video. For that one, you will need the table, and we'll see how we do. This first one here, so HSO3 minus as an acid. So on the table, we're looking for it on the acid side. I pulled up the table for us here. HSO3 minus is way down here. So we have HSO3 minus on the acid side, right? We see that it's in equilibrium, so we see that we're definitely in the weak section. And because we're fairly low down the table here, it's a fairly weak acid, right? So on the table here, I'm just going to copy that equation. So SO3 minus, on the table it's weak, so it's equilibrium. It ends up forming H plus and SO3. I go down by an H and I go down by charge, so this one's going to be SO3 minus 2. For the acid side, how do we get from the simple to the complex equation? Remember, it's almost like what we're going to do is we're going to add water to both sides. And effectively what that does for us here is it shows us not only is the HSO3 minus going to lose the proton, basically going to separate from the SO3 minus, it shows us who does the proton go to. In this section, HSO3 minus has a football. The H plus gets passed over to water. So that means water is my other chemical here. We're going to still be in equilibrium because we're in that weak section. The SO3 minus goes down by a charge and goes down by an H, and the water is now picked up, that H plus there. So that is the complex equation here. Again, we can refer to the H plus as a proton as a football. The proton gets passed over, and now it's water that's actually holding onto the H plus. That is the complex equation that answers the question, but you can actually analyze which are your conjugate pairs here. Well, this one wants to act as an acid. Although water is amphiprotic, water could have been acid or water could have been base. In this case here, water is willing to take that proton from SO3. So basically, the HSO3 minus passes the football over. Now the SO3 minus is without, minus 2 is without the proton, so it's now the base. And then the water that now currently holds the football is now the acid form. We always have two conjugate pairs. Conjugate pairs are on opposite sides of the table here, so that we can have one acid and one base on both sides. Let's do the other case here. We have HCO3 minus. Again, I chose some that were harder, right? They have an H, they have a negative charge. This could have been amphiprotic, but they want this one here as a base. So on the table, I'm going to look down the base side, and I'm going to look for this HCO3 minus compound. I see CO3 minus, nope, HCO3 minus, no, that's on the acid side. I'm looking for HCO3 minus on the basic side. So if you read it right to left, the base side says, as a bronze Lowry base, it accepts a proton, it grabs the H plus, and forms H2CO3. So I'm just going to sort of reverse that reaction there. Starting with HCO3 minus, basically it's going to pick up a proton. It's in that weak section, so it's in equilibrium. Now we're going to go up by an H, go up by a charge, and form carbonic acid. This is again simplified on the table. How do you get to the complex form? It's like adding an OH minus on both sides. For the acid side, it's like adding a water. For the base side, it's like adding OH minus. So therefore, my complex equation is therefore written HCO3 minus, H plus and OH minus will end up forming water. This is going to be in equilibrium. We're going to have carbonic acid form, and then it's actually the water that's actually going to drop off the hydroxide. We still managed to release the characteristic base particle, but we really didn't have to have an OH ourselves. So via that one proton transfer, currently the water has the football, and water is going to donate the football over. Water this time is acting as an acid, and the HCO3 minus is acting as a base, because that's what I wanted it to look like. Then the H2CO3 is then currently holding the football, so this is now the acid form, that's the conjugate acid, and the OH minus is the conjugate base. Again, we form two conjugate pairs here, one on either side. You have to have one acid and one base on both sides of the equation. All right. Now, part 2 of this question here is a little more interesting. Because both of these are amphiprotic, both of them potentially could be acidic or basic. Both of them could toss footballs. Both of them could receive footballs. Again, the choice is going to depend on who's better as an acid or who's better as a base. Because this table here only tabulates for us the acid strength, we're going to mainly compare their ability to be acid. So what I'm going to do here, it wasn't immediately obvious who's acid and who's base. Let's look for HSO3 minus and HCO3 minus. We already had HSO3 minus. I'm going to find HCO3 minus a little bit lower on the table. So no doubt both of these can be acidic because they're both on the acid side. They're both technically in the weak section because they're both equilibria, but relatively speaking, remember the stronger acids, it's increasing strength going upwards. So if both of these were willing to give off a proton, who's better? You can actually utilize this Ka constant. We'll see more in tomorrow's lesson here. The Ka value describes products over reactants. It describes how far this equilibrium pushes over. This Ka value, albeit small, it's a little bit bigger than this other one here, is 10 to the negative 11. So this reaction here happens a little bit worse. So HSO3 minus is the stronger weak acid. I know it's still a weak acid. I know it's still equilibrium, but it's stronger than HCO3 minus. So though both of them could be acids, this one here is the stronger one. So therefore, this gets to be the acid. The HCO3 minus says, fine, I'll be the base. And therefore, we just do the one proton transfer again. HSO3 minus is going to toss the football over. The HSO3 minus goes down by an H, goes down by a charge. This now ends up forming SO3 minus 2, and the HCO3 minus is now grab the football. It goes up by a proton, and it goes up by an H, goes up by a charge to form the H2CO3. You'll notice we had to compare the acid strengths here. This one here actually has a bigger Ka value. And I'm just going to just hint at this here. We'll do a little bit more in tomorrow's lesson. The Ka value, the equilibrium constant, this essentially is KeQ. The A is just for, it's an acid equation. The K value for HSO3 minus was 1 times 10 to the negative 7. So 1.0 times 10 to the negative 7. For the HCO3 minus, which could also be the acid, this one here was 5.6 times 10 to the negative 11. All right. Now, one added note here, I've already decided just based on acid strengths who's going to be the acid. You could have actually compared basic strengths as well. You could have said, well, both of these are willing to accept the proton. Who's more willing to accept the proton? We have the HCO3 minus. We also have the SO3 minus a little bit higher up on the table. Remember, the stronger my partner is as acid, the weaker I am in coming backwards. So in this case here, the H2SO3 would be even better at coming at HSO3 minus. HSO3 minus will have a really hard time going backwards. As I go down on the table, if I compare the basic strength here, H2CO3 here is not as good as an acid, so it doesn't push forward as easily. That means my partner has an easier chance. We actually have increasing base strength going down this way. So if you wanted to compare base strengths, you could say who is more willing to accept a proton. We're actually going to see that the Kb value is actually a little bit bigger, and that just sort of concludes the same. This is the base. Since it gives us the same answer anyways, we're just going to always compare acid strengths. That's going to give us the same answer. Now, what's interesting is we've now formed the conjugate acid of HCO3 minus. We've now formed H2CO3. It's currently holding a football. We know everything is at equilibrium right now. Both of these have been weak, right? This is a weak acid and a weak base equation. None of this is going to go one way. Meaning, H2CO3 actually has the ability to actually toss the football back over. It can likewise be the acid. The SO3 minus would then therefore be the base. We can compete. At first, the HSO3 beat out HCO3 minus. It was able to toss football. Now the acid is going to actually fight against H2CO3. It's possible I've now made an acid that's stronger than me, but let's just check our table here. I think that's what's happened. If I check the H2CO3, H2CO3 itself is an acid. H2CO3 has a Ka value of 4.3 times 10 to the negative 7. So the Ka of 4.0 times 10 to the negative 7. All right? So, sorry, 4.3 times 10 to the negative 7. All right, so although the HSO3 minus definitely wins HCO3 minus to be the acid, it's now created a conjugate acid that's even better than it. This 4.3 number is actually bigger than this one. So I always think of this as a sort of volleyball game here. At first, the HSO3 won. We had predicted this is going to be the product that ends up forming. And now I have a volleyball game between one team is weaker and the other team is even better at tossing the football back. In this case here, I'm ending up forming a stronger acid. Both acids on either side are trying to donate a proton, but if the H2CO3 has a higher Ka value, it's going to do the job better. Naturally, you would say, oh, that side's favored, that side's the winner. But remember, if they do their job better, this guy passes the proton back better. If I have a stronger team, I'm going to imagine that the ball lands on this side of the court more often. I'm going to just flesh this out for you here. Since the Ka for the product acid, for the H2CO3, ends up bigger than the Ka, the constant for the HSO3 minus, I have the stronger acid, the stronger team on this side. We're going to have the ball land on the reactant side more often, and we can actually say then, therefore, we have more reactants at equilibrium. And it's just a tricky wording here. Usually when we say we have more of one side here, we say reactants are favored. They're not favored in the sense that that side has the stronger acid. This side actually has the weaker acid. But it's because the H2CO3 here is better at doing its job, the ball lands on this side more often. Even though we will be eventually at equilibrium, we're going to have the reactants being favored. We're going to have way more reactants because the H2CO3 was better at its job. Okay. Tomorrow we'll come back, look more so at Ka. We'll talk about how we calculate Kb, and I'll actually give you a way to actually calculate what the Keq value should be here. All right. For today, just starting into a little bit more of the math here, I want to introduce to you one special equation. That special equation, if you completely blank on your test here, the special equation here is actually this equation here, directly for water. Right? So this one here is actually section 4.6, talking about Kw. Right? So out of all the equations I can look at here, I'm going to specifically look at this one equation. This equation here is just plain old water. The simplified equation says, well, water is on the acid side here. It can donate a proton. It's weak, right? It's not very good at going forwards. It becomes H plus and OH minus. This reaction can be called the self-ionization of water. Also sometimes referred to as the auto-ionization of water. So essentially what this reaction tells me is I could have gone to the tap and I could have gotten just tap water. I would imagine that this compound, the whole beaker here, is just filled with this H2O groupings, which predominantly there are. But what ends up happening here is just water by itself. It doesn't need any other chemical. Water has this slight ability to ionize itself. Water has the ability that every now and then you might have a lucky water particle that actually does the forward reaction. The water actually rips into H plus and OH minus. Now, how well does it do it? Being in equilibrium, being a weak acid as expression right now, I can look up the Keq. Because the Keq in this case here is specifically for a water reaction, I'm going to change this subscript here. I'm going to call it Kw. Okay? It's the equilibrium constant for water. What else do we know about Keq? Keq is supposed to be products divided by reactants. If this constant is much bigger than 1, it means products are favored. If it's much less than 1, it means reactants are favored. All that is true from chapter 2. In this case here, they're giving me the value on the table. Kw actually has a really small number here, 1.0 times 10 to the -14. Not only do we see on a table, if I'm on the acid side, I want to be higher up on the left side to be strong. Water is actually the last one down here. So this product over reactant ratio, this Kw, is given to me as 1.0 times 10 to the -14. I would memorize that number. This will do us good in the long run. But because this number here is so tiny, since this Kw is so much less than 1, we know reactants are favored. We know that although, yes, water has this ability to form H plus and OH minus, at equilibrium, we predominantly have a lot of water. Just like in our solubility chapter, it's a little bit hard to appreciate because water is actually in the state liquid. It's only aqueous ions that we can sort of track changes with Le Chatelier, things like that. Liquids here are actually ignored in the expression. So if I try to do a Keq in the expression here, basically I would have Keq, or Kw, is the product concentrations. H plus is aqueous, OH minus is aqueous. I would have naturally went divided by 1, right? But divided by 1 doesn't change anything, and therefore, Kw is just this expression. At 25 degrees, we actually have this constant, right? So far, we've reintroduced here KEQ is the equilibrium constant. It's a number that describes whether products are favored or reactants are favored. Because at 25 degrees, numerically, this value here is very tiny. It tells us we have actually very few H plus and OH minus in comparison to water. If you actually try to measure the constant composition of water, it's some 55 molar. So it's a huge, huge number, whereas the H pluses and OH minuses we'll be dealing with typically 0.1 molar, 2 molar, 3 molar, right? It's not going to be anywhere near as big. But what's really nice here is water has this ability to self-ionize. This actually gives us a nice mathematical link. If you know H plus, and we know that the constant is 1 times 10 to the negative 14, I can just solve for OH minus. Or vice versa. If I know the OH minus, water is going to self-ionize and it's going to regenerate a little bit H plus, so that when these two things here multiply, this is all at 25 degrees, it gives us a nice connection between H plus and OH minus. So let's just do an example of this here. Let's start off with 6 molar hydrochloric acid. Okay. For part 1 of this chapter here, we're going to mainly be dealing with strong acids because I don't necessarily want to deal with ice tables just yet. We'll come back to that later on. But HCl by itself is a strong acid. The 6 molar part tells you it's a fairly high concentration. Okay. So as usual, we want to start off with an equation if we can. I have HCl. This is one-way arrow. It's strong. It ionizes to become H plus and Cl minus. If I start off with 6 molar HCl holding hands, because we are one-way reaction, it completely separates. We're going to get 6 molar H plus and 6 molar chloride. We're going to see later on chloride is a spectator ion. Don't worry about that's in solution. What I care here is actually the 6 molar H plus. So in my container, right, we have it labeled 6 molar HCl. Basically, the HCl's are no longer holding hands. The HCl's have been leveled by water. We said that last day. Basically, I have 6 molar worth of H plus. Really, really, really acidic. What the Kw expression tells me is, wait a second, this HCl here is in solution, is aqueous. I also have water in the background. And water always has this ability to self-ionize. Water can regenerate a little bit of H plus, regenerate a little bit of OH minus. And what's actually going to happen here, even though we are in a heavily acidic solution, the water will definitely self-ionize. It's going to produce yet more H plus, but recreate the OH minus so that your H plus multiplied by how much hydroxide there is, it ends up always hitting this constant here. Okay, so let's just try it out. We now know that the Kw is H plus. The amount of extra H plus that the water self-ionizes is really minimal, but let's do our equation here. Because we also have water in the equation, it's not the equilibrium constant. This is not even an equilibrium expression. But because water is present and water forms this equilibrium with H plus and OH minus, Kw is going to be the H plus multiplied by the OH minus. At 25 degrees, our value is 1 times 10 to the negative 14. Like I mentioned, memorize that number. If my H plus is 6 molar, I'm expecting it to be really, really heavily acidic, fine. How much will the water self-ionize to recreate hydroxide? Now, it's a little bit weird. Well, we're in an acidic solution. Why do we want hydroxide? It's just natural that hydroxide is not going to be 0 because it still has to hit some positive number here. Now, I would expect hydroxide number will be very tiny. OH minus here, let's go 1e negative 14 divided by 6. This gives me here 1.7 times 10 to the negative 15 molar. Okay? So, imagine starting off, we had 6 molar HCl. That self-ionizes, we get 6 molars worth of H plus, a ton of acid particle. Water is going to realize, wait, I need to always make sure there's some hydroxide around. When water breaks up, not a lot of water breaks up because the hydroxide I end up forming is in the 10 to the negative 15. It's like 0.000, lots of zeros before you get to the 1.7. Right? So now we have a sort of different interpretation. We know we're in a heavily acidic solution. An acidic solution doesn't mean I only have H plus. As long as I have water, which I always will have, it's aqueous. An acidic solution is just one in which where your acid concentration is bigger than the base concentration. Right? Looking at the numbers here, our strong acid provided for us 6 mol H plus. Water, even though it's self-ionizing, is trying to replenish. Water reforms some OH minus just by self-ionizing, regardless of the HCl. but how much it ends up forming is way small. So 1.7 times 10 to the negative 15, right? So a conclusion there is every acid or base solution will always have H plus and OH minus. It's just more so the balance between, do I have more of the acid form or more of the base form, that makes me overall acidic or basic, right? Let's do an example on the basic side here. Let's take 2 molar strontium hydroxide. Usually I tell people you're going to save yourself a lot of grief, a lot of hassle. Anytime you're given a chemical, ask yourself, what is this? In this chapter, is this an acid? Is this a base? Is this strong? Is this weak? Depending on your answer in that case there, it'll specify what you need to do next. In this case here, at first I would say this is a salt, right? This one here is a ionic compound, right? You can check your solubility table. This is actually a fully soluble salt. Remember, we had added in yesterday's lesson, because a strong base, like let's say O minus 2 as an example, because a strong base one-way arrows and forms hydroxide, I basically then added in, if I have a soluble salt and it's able to 100% form hydroxide, I'm going to classify them also as strong bases. So I'm not going to find these ones here, ionic compounds, on my acid-base table, but because these ones here, I know they're completely soluble, let's write that out. As a salt, this one-way arrows become strontium ions and 2 hydroxide ions, just like the strong base, like O2 minus, just like it one-way arrows and forms hydroxide, so my salt also one-way arrows and forms hydroxide. We're going to classify this as a strong base, add it to that strong base list. So currently it's strong base, it's a one-way arrow. We have a 2 molar solution here. We're going to follow our mole ratio here. It's a 1-to-1 ratio, so we get 2 molar strontium ions, 1-to-2 ratio. We get 4 molar hydroxide ions here. We don't really care about the strontium. It's just going to be a spectator for now. We now know we're in a heavily basic solution. It's 4 molar hydroxide. So imagine with me here. This one here could have come as an ionic compound like SROH2 as a solid. Basically what you do is you just drop this in. As you drop it in, it starts breaking up, it starts forming those strontium ions, it starts forming the hydroxide ions to an extent where the concentration of hydroxide in here, the OH minus is actually 4 molar, right? We already said this is a strong base. We expect the pH value to be fairly high, right, into that basic region. But because we are actually in a water solution, water always has the ability to self-ionize. Water will recreate some H plus and OH minus in a 1-to-1 ratio and actually self-ionize to replenish a little bit of acid. We're never going to have a solution, basically having a water background, that only has OH minus or only has H plus. Now definitely in this case here, because we have a lot of OH minus, I'd expect the H plus to be fairly minimal. Let's have another look here. So the Kw is equal to the H plus times by the OH minus. Kw is a constant you can memorize at 25 degrees, 1 times 10 to the negative 14. I don't know how much it self-ionizes, but by the time you're at equilibrium, the H plus multiplied by the hydroxide at this point here has to give you 1 times 10 to the negative 14. Let's take that 1e negative 14 and divide it by 4. 1e negative 14 divided by 4 gives us our H plus as expected, super tiny. It's not that a basic solution can't have H plus. Water will always self-ionize, but we can classify this solution here as strong base forms a very basic solution. That's because the hydroxide concentration is bigger than the H plus. Looking at your numbers here, 4 molar of the hydroxide here, H plus that gets self-ionized recreated by water is only 2.5 times 10 to the negative 15. All right? So because water has this ability to self-ionize, it can make sure that there's still acid particle in a basic solution, still there's some hydroxide in an acidic solution. It's just the interplay of which one's bigger that matters. Okay. Definitely, when you start looking at this expression a little bit more, there's one other way this question can be worded. So that's the sort of acidic or basic example. What if we're interested in a neutral example? A neutral solution here is neither acidic or basic. A lot of compounds are not acids or bases. It shouldn't surprise you then. Well, H plus is equal to OH minus. It's not that I can't have acid or I can't have base particle, but if I have equal amounts of both sides, they sort of cancel out. So let's go to the tap here and let's just get water solution, right? So I would expect predominantly it's just water. We had just said water has the ability to self-ionize. Water is in equilibrium. It's a weak acid. It's going to become H plus and OH minus. The K value for this, KEQ, we call it KW, is 1.0 times 10 to the negative 14. I'm going to emphasize I'm at 25 degrees right now. Okay. So we can write out the Kw expression here. So far, this is the simple expression. So therefore, my Kw was just H plus times OH minus. I could similarly write out the complex equation for the acid equation. It's like adding water to both sides, right? Add water to this side here, add water to make that a hydronium here. Therefore, I can write the complex equation to a different color here. Water in the presence of water, well, I could say 2 water there. It becomes hydronium, H3O plus, and an hydroxide. But because these are always formed in a 1-to-1 ratio, even if I wrote that 2 water, I'm going to emphasize that's a liquid. Because it's a 1-to-1 ratio, I would expect to have equal amounts hydronium and equal amounts OH minus. That's always going to be neutral. I don't have a problem with Kw here, because if I do Kw, it's product over reactants for this special water equation. So let me just write this down here. This one here is basically KQ4, the self-ionization of water. In your question, you may be dealing with some random acid, some random base, but I know that in the background there's always water, and water will always have this equilibrium in the background. So if I try to do a products over reactants, this time it's going to be hydronium times hydroxide. It's a 1-to-1 ratio, so there's no powers there. Even though I would have did divide by water squared, again, water is a pure liquid, we ignore pure liquids. So sometimes you'll see the Kw expression written just H plus times OH minus. No real surprise, we already said H plus is synonymous with hydronium, basically gets hydrated complex with water. Those two multiply always has to give a constant, and this constant here is not 0. So that's why water always needs to self-ionize. Let me just write this down in words here. Because this constant is not 0, it's tiny, right? Water always self-ionizes to reform some H3O plus and OH minus regardless of what acid or base solution I'm dealing with. Right? Again, we can make a note here. We had said this one here is tiny, so this means reactants are favored. It means we don't have a lot of product ions in this case. All right. All right. If you look at this equation, Kw is equal to H plus and OH minus. We just did 2 problems with this. We did a situation where, I added in 6 molar HCl. The H3O plus has gone up. Because the Kw always has to hit a constant, Kw only changes with temperature, the hydroxide would drop. Right? Then I would have more acid than base, acidic. In the other question, what we did is we started off with base solution. I did 4 molar hydroxide. If I increase hydroxide, then the H plus has to drop for me to make sure I multiply to give the same constant. That's generally true. These two are usually inversely related. So let's write this down here. These ones here are inversely related. Right? When one goes up, the other has to go down so that we multiply out to give the same number. But the caution here is inversely related given the same temperature. Okay? If we're at totally different temperatures, all bets are off. Okay? So case in point here, let's say we are at 25 degrees, so we know the constant. Let's say we actually have a neutral solution. They can refer to a neutral solution as like a pure water solution. I just have pure water. I just have a neutral water solution. That word pure just means neutral. That implies, like we said earlier, the H plus has matched up to the hydroxide. Well, even at 25 degrees, we still have to hit Kw. So Kw as being H plus times hydroxide. If these two have to be equal, let's just call both of them x. 1.0 times 10 to the negative 14. How much x of H plus and how much x of OH minus would we have here? The x is just going to be the root of 1e negative 14, and this one is going to be, your calculator might just spit off 10 to the negative 7 like that. I always got confused when I saw that. You can think of scientific notation. This basically means 1 times 10 to the negative 7. Right? They're just giving you the order of magnitude. They're telling you the concentration is 0.00001 molar. Okay? So when you went to the tap and you grabbed the glass of water, I expect the majority of those is just H2O. Everything is waters together. Again, from the density, the molarity is about some 55 molar or so. But to a very slight degree, because there is a constant here, water has a very, very slight chance of actually forming a little bit of H plus, a little bit of OH minus. Even in a neutral water solution, I have acid, I have base particles there. It's just that they're equal and they're not a lot. Okay. Let's say what I do here now is I take that water here. Right now we're at 25 degrees. Let's heat this water. what I want to show you in this self-ionization of water equation here, this water equation is actually endothermic. So let's take the full equation here. 2 water, it actually has the heat term on this side. No real surprise because usually a decomposition here, dissociation requires endothermic. I'm going to tell you that it's actually endothermic. Let's see if we can make some predictions for us here. So that's just the water equation again. Right? I haven't added in any additional acid or additional base. This is the equilibrium that's been established. So far we've been saying the amount of H plus in the base is actually really, really low. Let's say I go from 25 degrees and let's say I now heat to 50 degrees. Okay? As I heat it up beyond 25 degrees, because we are in equilibrium, we can do Le Chatelier again. As I heat this temperature up, sure, the whole box heats up. One easy way to predict the shift was to look at the heat term. The heat term goes up. This is going to then shift towards the right side. Well, what happens then is as I heat to 50 degrees, let's just write this out here. My stress was I increase the temperature. The equilibrium, how does it going to respond? The equilibrium is going to shift right. It's going to shift towards products. And what's going to happen then is the H plus, H3O plus is going to increase, and the OH minus is going to increase. We can actually use this terminology. When your H plus increases, the solution gets more acidic. Right? Acidity is a measure of how much H plus is around. The more H plus you have, the more acidic it gets. Wait, acids are sour. The next time you boil water, does it suddenly sour on you? Well, no. The water just tastes like normal. It tastes neutral, whether it's at 25 degrees or 50 degrees. Turns out because of this nice mole ratio, every time you create an H+, you also create hydroxide. As this solution is getting more acidic, it's also getting more basic at the same time. That's a little bit strange because earlier we said, wait a second, when we were getting more acidic, when one was going up, shouldn't we get less basic? In this case here, the pure water, just keep it as a different sort of scenario here. I'm actually changing temperature. As I change temperature, the Kw value doesn't need to stay the same anymore. I can get more acidic and more basic at the same amount, and therefore I can still remain neutral. Right? I can actually predict for you here what happened to Kw. I now know my Kw is not going to be 1.0 to 10 to negative 14 anymore. The Kw, which is supposed to be H plus and OH minus, or hydronium times hydroxide, right? It's synonymous anyways. We have a situation that when I heat it up for an endothermic reaction, we end up generating more H plus, more hydroxide. These values here are now bigger, but by the same amount, we are still neutral. It doesn't suddenly sour on you or become bitter just because you heat it up. But because both of them have changed in the same direction, this time your Kw is actually bigger. So the Kw at 50 degrees is bigger than 25 degrees. So it's actually this constant that's changed. Remember, this constant only depends on temperature. Well, if I'm not at 25 degrees anymore, I can't use 1 times 10 to negative 14. So those are the two main styles. Usually we will be at 25 degrees. So usually you can just use 1 times 10 to negative 14. Every now and then they try to throw in a quick little change on you and they say, okay, well, how can pure water have a pH of 6? I thought that was acidic. We're probably not at 25 degrees. More on the pH scale in a later lesson, but that's how we're going to start doing the math here. Remember, we can totally still be looking at solutions. I have added base in solution. I have added acid in solution here. It's just that there's also water in the background, and water has this ability to self-ionize. Okay, so have a look at your problems and let me know if you have any questions. Thanks, guys.